Hi everyone, this is Maths for Uni. This is the worked solution to question 6 and question 7 from lecture 7 of our Udemy course. If you find this content helpful, then please consider liking and subscribing, as well as checking out our full Udemy course, of which the link is in the description. Question 6 says, the dihedral group D2n has a rotation r with r to the n equals e, and a reflection s with s squared equals e. R and s are related by SRS equals r to the minus 1. It asks us to state all of the 2n distinct elements of the group in a systematic fashion. So to start with, we've been told that there are 2n distinct elements of the group D2n. We can get n of them by just using rotations alone. We can have n elements which are e, r, r squared, all the way up to r to the n minus 1, since r to the n goes round back to e at the beginning, and this gives us n distinct elements. Then we can notice that we can get another n elements just by including a reflection on each of these earlier rotation elements. So we can get another n by doing, let's say, having s on the right-hand side of each of these above elements. So we can have s, because e times s is just s. We can have rs, r squared s, all the way up to r to the n minus 1 times by s. We could also put the s on the left each time, but it will turn out that we get the same kind of thing from these elements. How can we be sure that these are all of the elements? We've written down 2n elements, and we know that the group has 2n distinct elements, but even if we trust that, how can we be sure that all of the elements we've written down are in fact distinct? Could it be the case that r is the same as r squared s, potentially? We won't demonstrate this in full, but we'll try and remove any doubts that you may be having. For example, why can't we multiply by s again in the same way that we did above? We got these n elements by multiplying these elements by s on the right. If we do this again on the right to these elements, then we'll have s squared, rs squared, r squared s squared, all the way up to r to the n minus 1 s squared. But we were told that since s is a reflection, applying it twice is the same as doing nothing, i.e. s squared is equal to e. So this set of elements is really e, r, r squared, all the way up to r to the n minus 1, since each of these s squareds is really an identity. These are the earlier rotation elements that we already have in our group, and so doing this will give us no new elements. How about multiplying these elements here by an s on the left? Will this give us any new distinct elements? This would give us the set s squared, srs, sr squared s, all the way up to s r to the n minus 1 s. The first term gets immediately simplified by s squared equals e. The second term is interesting. We've been told that the rotation r and the reflection s are related by SRS equals r to the minus 1. And so this element here is r inverse. Can we simplify the other terms using this same result? SRS is r inverse. We have SR squared S and all the way up to SR to the n minus 1 S. If we have this result here, can we find SR to the K S more generally? Well, indeed we can, by noticing that if we multiply SRS together K times, so we have these SRS and we have K of them, then we have these S squareds that appear between adjacent terms. Since S squared is equal to E, we will have all of these cancellings in the middle, giving us an E each time, which disappears because it's the identity. The only S's that remain are the S's on the end, i.e. we have an S here and an S here, and what will be in between is all of these R's that we've picked up. And since there are K lots of this entire term here, there are K R's. So we have found SR to the KS in terms of SRS. But since we have this relationship above that tells us that SRS is r to the minus 1, therefore we have r to the minus 1 to the power of k, which is r to the minus k. Hence, all of these terms here, by using this result repeatedly, are e r to the minus 1, the next one will be r to the minus 2, because the SR squared S becomes r to the minus 2, and then so on up to r to the minus n minus 1. Are these a set of new elements? Well, no, because, for example, r to the n is equal to e, and so if we multiply both sides by r inverse, we have r to the n minus 1 times r inverse is e times r inverse. The left-hand side is r to the n minus 1, and the right-hand side is r inverse because of the identity. So notice that this r inverse that's here is really r to the n minus 1 that we already had in our original rotation elements in here. In fact, if we continue, we will find that our elements are actually just all of the rotation elements that we had before. By applying r inverse inductively, this is r to the n minus 2, and this ends up being r here. And so really, we just have the same rotation elements as earlier, e, r squared, all the way up to r to the n minus 1. By considering similar arguments, we can find that we only have the 2n elements that we wrote down above, and there are no more, and they are all distinct. So either way, we end up with the 2n elements for D2n as being e, r squared, all the way up to r to the n minus 1, and then we have s, rs, r squared s, all the way up to r to the n minus 1 times by s. And this gives us our 2n elements of our dihedral group D2n. Now, in this video, let's also discuss question 7, because it links quite nicely to the question that we've just discussed. So question 7 says, using the result of the previous question, show that D4 is an abelian group. Show that D6 is not an abelian group, however. Recall that a group is abelian if all of the elements of the group commute, so that it doesn't matter which order the operation occurs in, i.e., a group G is abelian if for all GH elements of the group G, we have that GH equals HG. Let's start by writing down the elements of each of the groups that we're considering in this question with the help of the previous question. Firstly, we have D4, which corresponds to n equals 2, and from the previous question, the elements are E, R, and then R squared goes back to E, so we have S and RS. Similarly, for D8, we have that n is equal to 4, and so we have the elements E, R, R squared, R cubed, at which point R to the 4 gives us back E, and then S, RS, R squared S, and R cubed S. We can start by showing that D4 is indeed abelian. We need to take all combinations of the elements and show that they work both ways around to give the same result. Trivially, this works for the same element. So if we're working in D4 to start with, EE is the same as EE, RR is the same as RR, SS is the same as SS, and RS is the same as RS times by RS. This is always true because we're taking the same element, and so the order does not matter. Now, if we consider distinct elements, we notice that anything will automatically work with the identity by definition, because ER is the same as RE because it's just R. Next we have ES is the same as SE because they're both S, and E with RS is the same as RS with E, which is just RS. We need not check E with E because we had it the same above in here. Again, it might help to remind yourself that these are the elements of D4, and then next we only have the last ones to check, which are combining R with S in both ways, R with RS, and finally S with RS, because we checked everything with itself and everything with the identity. So we need to check, and I'll put question marks here to show that we haven't actually demonstrated these yet, that RS is the same as SR, that R with RS is the same as RS with R, and that S with RS is the same as RS with S. To check these three results, we'll need that SRS is equal to R inverse for any dihedral group. Notice that because R squared is equal to E in this particular dihedral group D4, R inverse is equal to R. So to check firstly that RS is equal to SR, consider moving everything onto one side, i.e. putting this R over here as an R inverse and putting this S over here as an S inverse, and then we need to check that we get E, i.e. we want to check for the first one that we have RS, R inverse, S inverse as being equal to E. Well, we can now, luckily that we've done this, compute the left-hand side. RS, R inverse, S inverse is RS, RS, because R inverse is R, as we have here, and S inverse is always S in any dihedral group, because s squared is equal to e. Then RSR, or rather instead, apologies, SRS from here is equal to R. And so we have the first R, which is here, and then the SRS gives us another R. This gives us an R squared, and then finally using R squared equals E gives us E. And so we've checked that RS, R inverse, S inverse gives us E, and so 1 certainly holds, which implies that this certainly holds. Next, to check that R times RS is the same as RS times R, we can move everything across and instead consider R squared S, R inverse, S inverse, R inverse, and check that we get E. So we have, let's have a look, that R squared is equal to E, so we can ignore that. We have an SR inverse, S inverse, but again using R inverse as R and S inverse is S, we get SRS, and then the R inverse on the end here is also an R in this group, and so we have this, and this includes an SRS, which we can replace by an R, and so we have R times R from the SRS, which gives us R squared, which gives us E as we desired. And so therefore, R times RS is the same as RS times R. Now finally, we check this here. And so by moving everything onto one side, it suffices to check that. Let's have a look. Oh, actually, no. A faster way to do this is to notice that the left-hand side is already SRS by removing the brackets. So let's write this down. We have to check that SRS is equal to RS times by S. We're not yet sure of this. Well, the left-hand side is an R because SRS is R inverse, which is R. And the right-hand side, well, this is RS squared by removing the brackets, and S squared is E, and so we just have R. These two match up, and so indeed, this result is true. Hence, by checking manually, all elements commute with one another, and therefore D4 is an abelian group. Next, we want to show that D8 is not an abelian group, i.e. it's non-abelian. If this is indeed true, then it might be easier to prove since we only need to find two elements that don't commute with each other in order to break the fact that it would be abelian. Let's look at the most basic element that we can get from combining the rotations and the reflections. We do this because if we only consider the rotations on their own, or only consider the reflections, then we won't get anywhere, because these form cyclic groups on their own, i.e. the ER, R squared, R cubed is C4, and the group E with S is C2. And these are abelian groups on their own. And so we should combine rotations and reflections. The most basic element of this form is RS. And so we check whether RS is equal to SR. Let's try and show that in fact this is not true. In order to do this, we move all the elements onto one side, and so we have RS and then R inverse S inverse, we check that this is equal to or not equal to E. In this group, R inverse is equal to R cubed, because R to the 4 is equal to E. So, as a result, this expression here is RS times by R cubed for the R inverse, and in every dihedral group, S inverse is the same as S. From our earlier discussion of the previous question, we recall that S R cubed S, whenever we have an S sandwiching an R to the power of K, this will give us R to the minus power of the same thing, so R to the minus 3. In this group, R to the minus 3 is equal to R, again because R to the 4 is equal to E. Hence, this gives us that this is equal to R times R, which is R squared, and in this group, this is not equal to E. Therefore, by moving these things back to the right-hand side, we have that RS is not equal to SR. Therefore, R and S do not commute, which is enough to tell us that D8 is non-abelian. Hence, we have satisfied the requirements of this question. If you found this content helpful, then please consider liking and subscribing, as well as checking out our full Udemy course with plenty of other worksheet questions. The link is in the description. Thanks for watching, and goodbye for now.